Alright, so I'm going to attempt to do a full sketch of this function, 10 times the ln of x squared divided by x squared. So I'm going to go through all of the things that we've put together in this curve sketching unit so far, and we're going to do them all on this board, and we're going to gather up all the features, and then we're going to try and plot them onto a curve, or onto an xy axis, to see if we can approximate this curve. So I think I'm going to start with the x-intercepts, because that seems to be where we always start. So x-intercepts mean that the function is worth 0. So that's where the y value is nothing. So that means that this function has to equal 0. Well, you can see right away that there's a thing times a thing. That's my cases method. So either 10 over x squared equals 0 or ln of x squared equals 0. This is impossible. You can never get a 0 by dividing. This side, I'll need the anti-function for ln, which is exponentiate base e. So that would be e to the power 0. E to the power 0 is 1. Square root both sides, I get plus or minus 1. So I should have x-intercepts at x equals 1 and at negative 1. Okay, good. Task accomplished. So continuing on, I'm going to need the first derivative to do the max-min points. So this thing is going to be a product rule, and the second half of the product rule will require chain in order to execute it. So df by dx is going to be derivative of the first, leave the second alone, plus leave the first alone, then derivative of the second, but set up as a two-layer chain rule. So derivative of the first is negative 20 x to the negative 3. Leave this alone is ln x squared. Leave this one alone, 10x to the negative 2. Derivative of a ln is 1 over the argument, and then the derivative of the argument because it's not simple. So we're going to have to gather up some terms here. df by dx is, I'm going to put this into fraction notation, so I have negative 20 ln x squared divided by x cubed. And in this term, I have 2 times 10, which is 20. I have an x squared in the denominator from this term, an x squared in the denominator from this term, and an x in the numerator from that term. Now this reduces a little. One of these x's eliminates 1 power of x from the bottom, and an x squared simplifies to an x cubed. So I've accidentally ended up with a common denominator, which is encouraging. I have a power of 20 in both terms, so I'm just going to pull them out. 20, that will be, I'm going to pull out a negative 20 just for fun, leaves me with ln x squared in the first term and negative 1 in the second. And I'm going to write that as a thing multiplied by 1 over x cubed. Because out of max min, I have to set this thing equal to 0, so I'm already set up for my cases. So going through to get these cases worked out, either negative 20 equals 0, which is not a thing, or 1 over x cubed equals 0, which is not a thing. You can never get 0 through division. Or this one that remains, the ln x squared minus 1 equals 0. Kick the 1 over. Undo ln by exponentiating base e. So e to the 1. So x will be the square root of plus or minus e. Alright, now I'm going to approximate that as a decimal so that we know where to plot it. The square root of e to the 1 gives me 1.649 approximately. Okay, so I need to get my y values, so I have to put this x back into the original function. So f at the positive square root of e will be 10 ln square root of e squared divided by square root of e squared, which is going to be square root of e squared is just e, ln of e is 1, and 1 times 10 is 10. Square root of e squared is just e, and that gives us approximately 10 divided by e to the 1, 3.679. So I have a max or a min, I don't know which it is yet, at 1.649 on the x and 3.679 on the y. There's also one at negative 1.649, so if I have to work out the y values for that, make this negative, that would be negative, that would be negative. As soon as you square a negative, it becomes a positive, so I return the same y value. Alright, good. So I'm going to erase all of this except for the simplified version of my first derivative, because I will need second derivative in order to do the points of inflection. Let's get that off here. Alright, so I have a product rule. I have this multiplied by that. Just for simplicity, I'm going to park the 20 in there. That was my first derivative. So my second derivative, when I go to take that, is going to be a chain rule, or a product rule, sorry, because it's a thing times a thing. And this term is going to require chain because it's an x squared shoved inside a log. So my second derivative, df by dx squared, will be derivative of the first, which is going to contain a double layer chain, and then the derivative of this 1. Some space for that. Leave this piece alone, plus leave the front piece alone, derivative of the second part. Alright, so derivative of ln squared would be 1 over the argument, and then the derivative of the argument. The derivative of a negative 1 is nothing, so that goes away. Leave this piece alone, 20 over x cubed. Leave this part alone, ln x squared minus 1. This thing here is 20x to the negative 3. So negative 3 comes down, makes that negative 60 x to the negative 4. Alright, so I'm going to clean this mess up. In this front term, I have a 20 multiplied by 2. Actually, this subtract 0 doesn't matter. I'll just get rid of it. 2 times 20 is 40. And there's a power of x up top, an x squared in the bottom, and an x cubed in the bottom. In this term, I have a negative 60 times that, so subtract 60 ln of x squared minus 1 with an x to the power 4 in the denominator. One of these x's divides one of those away, and an x squared times an x squared is an x4. So again, I ended up with a common denominator accidentally, which is encouraging. So my second derivative then would be 40. Negative 60 times ln squared is negative 60 ln x squared. Negative 60 times negative 1 is plus 60, all multiplied by 1 over x to the 4. d2f dx squared is 40 plus 60 is 100 minus 60 ln x squared, 1 over x to the 4. So just like x-intercepts and max-mins, I need to set this thing equal to 0 in order to find my points of inflection, which gives me cases. So case 1 is either 1 over x to the 4 equals 0, which fails, or 100 minus 60 ln squared x, ln x squared equals 0. So that one will have solutions, but I'll need some space to do it. So clean that off. Throwing this 60 ln x squared over to the other side, I get this. Divide both sides by 60, I get 100 over 60, which is 10 over 6, which is the same as 5 over 3. Exponentiate base e to break a ln. So x will be plus or minus the square root of e to the 5/3. Now that's gross. So I'm going to approximate that to a few decimal places. E to the exponent 5/3 gives me 5.294. Square root that answer gives me 2.301. All right. I'm going to need the y values for that, so 2.301 goes into here. So f at 2.301 would be 10 times ln of 2.301 squared over 2.301 squared. .301 squared gives me 5.294. Ln that should give me 5/3 times 10 gives me 16.6667. And 2.301 squared is 5.294. So 16 point all the 6's divided by 5.294 gives me 3.148. So I have just figured out that I have a point of inflection at 2.301 on the x, 3.148 on the y. Now this plus or minus 2.301, so if I toss the negative in there, this has happened again and again in this function, that you end up with the same y values. So negative 2.301, 3.148. And that's because both of the x's are squared, so it doesn't matter what number you put in, doesn't matter whether it's positive or negative, it comes out the same answer. Alright, so I've got a list of features forming. It's just a few more left to go. So I've done intercepts, I've done max-mins, I've done point of inflections. That leaves me with domain/boundary errors and end behaviors. And then I should have everything I need in order to sketch this function. So if I'm going to talk about errors, the boundary errors or the domain ones, I have a function here that is 10 over x squared multiplied by ln x squared. So both those pieces generate boundary errors, and a ln can generate a domain error. So I have to consider both of those things. The rational part, 10 over x squared, has a boundary error when the denominator, x squared, equals 0. So that happens at x equals 0. The ln has a boundary error when the argument, x squared, equals 0. So therefore x equals 0. Okay, now they both landed in the same spot, so that means they either contribute to each other or they mask each other. So I'm going to have to check that by actually taking the limit as x goes to 0. So let's see. limit as x goes to 0 of 10 over x squared ln x squared. So I'm going to try a few numbers creeping up on 0. I'm going to try 0.01, 0.0001, and 0.000001. That's 1, 3, and 5 zeros. Alright, so 0.01 squared equals ln of that answer. It's negative 9.21 times 10 equals negative 92 divided by 0.01 squared gives me negative 921,034. Now I'd wager that's going to negative infinity, and it's doing it pretty aggressively. Try one more layer. 1, 2, 3 zeros and a 1 squared, and then ln of that answer gives me negative 18 times 10. It's negative 184 divided by 0.123 zeros and a 1 squared gives me negative 1.84 times 10 to the 10. So that's 18 billion. I think it's pretty safe to say that these numbers are going to negative infinity. So there's no masking. I ended up with a boundary error. So that means that there is an, I guess my list here, there is a vertical asymptote at x equals 0. All right. So now that we've got the boundary error under control, we just need to think about the domain error. Let's see, ln x squared has a domain error when x squared is less than 0. Now that's impossible. There are no real numbers where you square them and you get a negative as an answer. So there are no domain errors for this particular function. So you can clean that off. All right. So the last thing to deal with then are the end behaviors. So the limit as x goes to infinity of 10 ln x squared over x squared. I'm going to try 10, I'm going to try 100, I'm going to try 1000. So 10 times ln of 10 squared divided by 10 squared gives me, well, 10 squared is 100, so ln of 100 is 4.6 times 10 is 46 divided by 10 squared gives me 0.4605. Alright, I'm going to try 100. So 100 squared is 10,000. Ln of 10,000 is 9.2 times 10 is 92.103 divided by 100 squared gives me 0.00921. And if I try 1,000, 1,000 squared, ln of that answer is 13.8 times 10 divided by 1,000 squared gives me 0.000138. Okay, now looking at these numbers, it was 0.4, then 0.009, then 0.0001. It looks to me like these numbers are going to 0. So as x goes to infinity, f of x is going to 0, and they're all positive, so it's dropping from above. Okay. Now, same with the other features. If I try and do this as x goes to negative infinity, make this negative 10, negative 100, negative 1,000, these numbers just get negative before squaring them. So the negative goes away immediately. I end up with the same numbers. So it is irrelevant which direction I'm going. The thing seems to be settling on 0 from above. Okay, so I'm going to erase this. And I'm going to take a minute to make sure I have a pretty tidy axis. So I'm going to speed up here a little bit. Okay, so all my x features lie within 3 on the x-axis, so I'm going to label that 1, 2, 3, -1, -2, -3. All of my y values are within 4, so 1, 2, 3, 4. I have x-intercepts at 1 and at -1. I have a maximum at 1.6, that's about here, and 3.6, which is about here, and one in precisely the same position on the other side, that's about here. And to remind myself that those are maximums, I'm going to draw a line like that. Now you notice what I've done there. I don't technically know that they're maximums yet, but looking at the picture and looking where they're positioned, I have my suspicions. Point of inflection would be at 2.3, that's a little bit out here, and at 3.1, that's about here. And 2 points, let's go over a little bit, 2.3. Let's see, it's like there. And to remind myself that those are points of inflection, I'm going to draw myself a little twist line. Okay. Now I'm supposed to have a vertical asymptote at x equals 0. So it's either doing this on this side, or it's doing this on this side, or it's doing this on this side, or that on that side. So some combination. It could be doing this, it could be doing this, it could be doing this, or it could be doing that. I'm not really sure. As I go to plus or minus infinity, I am dropping down to 0 from above, so I have to get this sort of thing going on. So I'm going to look at my features, and I'm going to try and make some educated guesses here. The first thing I'm going to draw in is that I can see, based on these dots, that this must be a maximum here. It must come up and crest, like so. This is a terrible sound. I'm going to have the crest on that dot. Not too bad. And the same thing is going to happen on the other side. And I'm going to be very careful to make sure that it's curved. It's got to be curved down in that whole segment. At the point of inflection, instead of being curved down, it flips to curve up. So I'm going to draw it going like this. And you can see it settling down onto the x-axis. So I have satisfied this end behavior. The same thing on this side, curved down before the point of inflection and then curved up on the other side of it. Has satisfied that end behavior. All right. Now, looking at these asymptotes, there is no way for this function to turn back around and get up to an asymptote on this end of the axis without there being either another x-intercept and another max min. There'd have to be a turning point, and I don't have them, which means that I can't execute that maneuver. I can't do it on this side either. So the only option is to have it drop aggressively like so. So there you have it. I've drawn a curve that has max mins at this point and this point, has points of inflection here and here, has a vertical asymptote at x equals 0 as they're supposed to be, and has these end behaviors where it drops to 0 as x gets large in both directions. So if you can appreciate that once you get these things all on the list and you start putting them on the graph, there's only certain ways that you can connect the functions. So if you make sure that you only crest or trough at a max min, that you only switch curvature from curve up to curve down at a point of inflection, and you choose your asymptote traveling and your end behavior traveling based on where the rest of the dots are, you can reasonably easily connect the dots and the features in order to get your sketch. Now there is a second example on this page. If you scroll down and look at the notes, you'll see this one all written out. And then there's another one which I would encourage you to read through, which is just another example of how to put features on there. But otherwise, you are off to the practice problems. Good luck.